Any questions about that schedule that I've given you? Okay. I've also handed out the next homework assignment. So you've just submitted homework assignment number 2. I'm sorry, number 1 to Blackboard. These ones as well. You've just submitted homework assignment number 1. Number 2 is going to be similar, where the assignment will be exclusively things that you do as hand calculations. I'll ask you to solve it on just ordinary plain white paper or engineering paper, scan it to a PDF, and then upload the PDF to Blackboard. Probably homework assignment number 3, you're going to begin to use Microsoft Excel on the assignment. And so then on that, when you've used Microsoft Excel, you should include both your hand calculations and also the spreadsheet file that you prepare. So just basically upload all of your work that helped you to arrive at the solution. One of the things I ask you to do on homework assignment number 2 is to create a LinkedIn profile if you don't already have one. One of the things I'm eager to do is keep in touch with students after they've graduated and kind of share employment opportunities with them as they become available, and keep tabs on what their latest career advancements are. So that's why I ask you to, if you haven't already, create a LinkedIn profile, and then once you do, connect with me on LinkedIn. So I've given you the notes for today's class. Any questions before we jump into the material?
Could you tell us a little bit about the project that we're going to do at the end of the month?
The first project that you're going to do is related to optimization of a pumped storage electricity generation system. And I don't want to spend too much time because I've got a set of diagrams and photos that I think will help to make it more clear. But basically what you're doing is you're trying to find out what's the most amount of money that you could make based on balancing equipment costs, the costs of the electricity that you're going to use, the value of the electricity that you're going to sell. And so it's an optimization project where you're going to be using Microsoft Excel and the solver function, which is kind of a, it's like GoalSeek on steroids. So yeah, we'll get into that. I think in a week and a half I'll assign that to you, and then you'll have a couple of weeks to work on the project. It's the sort of thing where I think you probably, if you budget 5 hours for the project, that will probably be plenty. All right, now I've shown you this figure before, and does anybody remember what are the risks to a lender that makes it so that they want to charge higher interest rates when someone is asking for an increasingly larger loan? I enumerated some of the risks that they sense.
Risk of defaulting?
Okay, risk of default, and that's maybe the biggest risk, was the default risk. And what does default mean?
Not paying back.
Not paying back, right. So, but you're the same person whether you borrow $1 million or $6 million. It's not like you're any less honest. So why are they worried that you're not going to pay back if you borrowed more money?
Maybe your debt-to-income ratio.
Okay, very good. Yeah, it's simply because if you've got a lot of debt, you've got high payments, and those high payments are harder to make based on the amount of business that you've got on your book. And so they're analyzing maybe your past revenue history, or they're looking at your clients, and they're looking at the work that you may have lined up in the future, like your firm orders. And so whatever their evaluation is, as you ask for a larger and a larger loan, their perception of the risk increases, and so then the rate of return that they'd like to compensate for that risk also goes up. Another one of the risks that is compensated for is interest rate risk. And does anybody remember what interest rate risk is? What's that, Ben?
It's the risk that the interest rate will fluctuate either up or down, so you add a little bit in the beginning to account for if it goes down and you just hope that it doesn't go up because you could have made more money if you waited to lend the money out in the future.
Very good. That's exactly right. Just to refine one aspect of it, though, what is the bank worried about? Are they worried about that after they make the loan that interest rates will go up, or are they worried that interest rates will go down? They're worried that it'll go up, because if interest rates go up, then that's a lost opportunity for them. They'd love it if interest rates go down and they've locked in a contract with you at 5%, and then tomorrow interest rates go down to 4%. They'll smile and feel satisfied. But it's when interest rates go up. The real problem is interest rates go up oftentimes as a reflection of inflation. So they say that if you're in an inflationary environment like we are right now, it's good to have loans. It's good to own a house, well, to be buying a house and to be paying back the bank, because if you borrow money today and inflation is 10%, but your loan is 6%, then that basically means that the value of the home is increasing faster than the interest is accumulating on the loan. So in an inflationary environment like this, it's good to have a loan as long as you can make the payments. It's good to be in debt if you're paying back in the future with dollars that aren't as valuable as the dollars you borrowed. That's great. So again, this curve is largely related. It's mainly driven, I think, by default risk. So there's all these different projects a hypothetical company could do. There's many ideas for growth and new projects. And let's say that we knew, for example, on this list of potential projects, how much each one of them cost, and we had some estimate for what they might return. So their likely rate of return. And if we graphed that, the width of each of these bars refers to how expensive the project is. And we've sorted them from the highest rate of return to the lowest rate of return. So obviously, you would prioritize which project you invest in based on what is going to yield the largest rate of return. So I don't remember what A was. A was upgrade your computer network. So if you spend, looks like $600,000 to upgrade your computer network, then you're expecting that the rate of return is 35% per year for that. And so there's all these different projects you could do. And let's say that you had to borrow money in order to initiate these projects. Is it a good idea to borrow money to do project A if you have to pay 10% interest on that loan? Why is that a good idea?
You're going to return 35%.
You get 35%, but you're only paying 10% to the bank. So that's a great deal. You know, like what if there are two banks next door to each other, and one of the banks is paying on deposits. If you deposit to their bank, they're paying 35%. And the bank next door is loaning money at 10%. Well, you could just go to one bank, borrow as much as possible, go to the next bank and deposit it. That's called arbitrage. When you see something for a low price and you sell it for a higher price. And so here, basically what you're doing is you have an opportunity. You don't have the money to do the opportunity, but you can get it. You can get the money. You just have to pay 10%. And you keep the difference. You keep the difference between the rate of return in the project and the cost of the capital that's been acquired. Now, project B is a little less juicy, at least from a rate of return standpoint, because it only yields 30%, and you had to pay just incrementally a little bit more. At that point, the interest rate hasn't gone up much. But if we take this idea to the margin, project E is justified, but project F, to get the money for project F, you're at the point now where you have to pay 16% interest to the bank to get the money. But the project itself is also yielding 16%. And so you're turning over all of the value of that project to whoever you borrowed the money from. And so that project would not be economically justified. I mean, maybe there's other reasons to do the project, like good community relations, or you're providing jobs for people, and you want to be a responsible citizen of the area, or maybe you're doing it because there are environmental benefits that there's not a dollar value on, but still is important. But just strictly from profits and losses, F is not justified and G is definitely, like even if you just broke even, I guess F, you could take it or you leave it. You should only really do something if it's going to be profitable, but F at least doesn't lose money. Whereas on the other hand, G should be rejected because you'll lose money. The cost of the capital that you've acquired is greater than the value of the return. So minimum attractive rate of return is the idea that every business has, by virtue of where they're getting their money, some minimum rate of return that dictates whether they'll accept or reject a project. So some companies are cash rich, like Berkshire Hathaway. Has anybody here heard of Berkshire Hathaway? So that's the company that's run by Warren Buffett. And he's always complaining about how he's got too much money and not enough good investments. So he's always looking for big investments, big companies that he can take over. Berkshire Hathaway owns Dairy Queen, for example. They own shares in Coca-Cola. And
Special metals, don't they?
Mm-hmm.
oh, do they?
They do.
Okay, Berkshire Hathaway Special Metals. I did
Well,
not know that.
It's actually, Special Metals is owned by a bigger company, which is owned by.
Yeah. Yeah, there's all sorts of textile manufacturers, mobile home manufacturers. They're a holding company that has a wide range of rail, food, beverage. They're a company of companies. But the problem that Berkshire Hathaway has is too much money and not enough investment opportunities. Most companies have the opposite problem. They have to borrow money. And so those companies are going to be selecting which projects to undertake based on how expensive it is for the capital that they need to acquire. So they can go to places like the bond market, or they can sell shares in their company, or they can go to banks and get financing that way. There's a lot of different categories for the way that money can be raised. Preferred shares. There's really a lot of different ways that companies can raise money. And this is a formula that shows you how to calculate a weighted average. And this is something that I included on that concept inventory on the first day of class. Some people had the right idea on the concept inventory. Some people had never heard of the weighted average cost of capital. And so the way that the weighted average works is that how much any given category is counted is influenced by how much of the money you're getting from that category. So I've got an example here in a minute, but I wanted to show you this formula, and there's a different version of it. This one's based on a percent. So if you know that you're trying to borrow $1 million and 25% of your financing is going to come from a bank that has a certain interest rate, maybe 50% of your financing is going to come from bonds that your company sells at a different interest rate, and then the other 25% of your financing is going to be acquired through selling shares in your company. And the expected cost of that, maybe you have an interest rate. So this weighted average cost of capital can also be expressed either on a percent basis, or if you know the absolute number of dollars that you need to get from one source versus another. In the denominator, you add together all of the different components, and that's what makes it a weighted average, is that there is a weighting or an amount indicator that tells you how important each different category is. So one of the in-class exercise questions that we have today is another crack at applying this formula related to weighted average cost of capital, and it's just to lay the foundation for a homework problem that you've got. Any questions about weighted average cost of capital? Okay. We've looked at these formulas. I think the main ones that we've worked with so far have been, remember, future is present 1 plus I to the n, or present equals future 1 plus I to the negative n. this table is just expressing the same thing, but in the symbol column is where you find the ratio of what it's referring to. And so look in the symbol column on the first row. What it's saying is that f divided by p equals 1 plus I to the n. So obviously all you need to do to solve for f is just move p over to the right hand side of the equation. I think, what did we used one of the other ones in last class. Was it AP? Was it find A given P in the in-class exercise from?
I think it was find P given A.
Find P given A.
Yeah.
So it was this one. Okay, so I only gave you like one row in that in-class exercise, but let's just revisit what that was saying. It was saying P slash A equals 1 plus I to the n minus 1 in the numerator, and then in the denominator it was I 1 plus I to the n. Okay, so the way to use it, obviously, we have the unknown in the numerator because the easiest thing for us to do is just move the known A to the right-hand side of the equation by multiplying both sides, and so times some A value that's known. And you can put this into the calculator and keeping all of the precision so that the answer is going to be accurate to the nearest penny. You'd find out the value of this factor. And as we're going to see in today's in-class exercises, you can either use this, they call it the equation method, or there are factor lookup tables. This is the format the format of the table that's from one textbook. If you open up the homework assignment, there are two other tables. They sometimes look a little bit different, but they have the main idea. There's one table that's taken from the the formula manual for the Fundamentals of Engineering exam, and then there's another table that I just grabbed from a different textbook. But you can see that the common attributes that they all share is somewhere it's telling you what interest rate it is, because there's a different table for the 8% table compared to if you've got a 5% interest rates. If you actually look at like what F slash P says for the 8% table, it's going to be different from what it says on the, do you have the 5% and what other do you have, 4 and 5?
4 and 5.
So you've got the 4 and 5. You can kind of tell what the interest rate is by looking at this first one. If n equals 1, then the ratio of F to P is going to be 1.08 for the 8% table. For the 5% table, it's going to say 1.05. For the 4% table, it says 1.04. So it's pretty obvious in that sense. Where it becomes a little bit less obvious is for some of these other columns and as you get further and further down into the compounding. But the disadvantage of these tables is that they don't offer as much precision. Because if you look, for example, at this present worth column, there's only 4 digits there. And so if you're talking about millions of dollars, then using this factor is only going to allow you to be accurate maybe to the nearest $1,000. You won't be accurate to the penny. So my suggestion when you're using these is at the very end of the problem is where you do the rounding off. Don't round off in intermediate steps, but at the very end, revisit and ask yourself how much precision did you have in the factors that you were using, and then round off to the nearest 4 digits, or in this case you can see it's 5 digits. So let's just take a look at how these tables are applied. So if you deposit $5,000 into an account, so that's P. Remember, one of the strategies is to label on the problem statement the variables as we see them. So P is 5,000, the interest rate of 8%, so I is 0.08. The amount in the account after 10 years, so N equals 10, and we're trying to find the unknown F. And so what we would want here is we'd want to use the F F/P column. So F/P here, it's labeling that as a compound amount. And this was for 10 years. And so if we go down to row 10, the factor is 2.1589. And so we're going to multiply 2.1589 by the present value, which was 5,000. So if we express it as a cash flow diagram, you deposit 5,000 now. The unknown in 10 years is a future value. And so we multiply the present value by the factor and get that it's going to be $10,795 after 10 years. Okay. Or if we are discounting, remember last time I told you that compounding is when you're moving money into the future. So this was a compounding problem. The amount got bigger as you moved the money forward in time. Discounting is when the amount is going to get smaller. So here we know that the given amount, this F value of 50,000, is in 5 years, so N equals 5. The interest rate, 10% per year. Now we don't have a 10% table, but the factor, if you go to the 10% table, the factor is 0.6209. I'll give you in exams all of the factor tables that you'd need, and I'll post on Blackboard a lot of different interest rate tables that you can use for the homework assignments. This one I've remembered, I think, to include just a table in the handout itself for any of the interest rates that you need, but I'll put an interest rate table on Blackboard so that you've got it available if you need it. So here, 50,000 was in the future. We're solving for the present value. It's going to be less because it's moving to the left through the cash flow diagram on time. Okay, so we're going to get some practice with these today, these sorts of calculations. But I wanted to show you some of the standard notation approach. And this came up in class on Tuesday, where it's very unusual, but it was the fact that the future value is in the same year as the last annual series. And so let me show you the assumptions, for example, converting between a present value and an annual series. So the main thing I want to point out, remember, is that for it to be an annual series, the arrows have to be the same height. So that means that the amount is the same for it to be an annual series. There's no gaps, so it's a series of consecutive and unbroken payments over time. And then at time 0 is the present, but because of the end of period assumption, we don't see the first effect of the annual series until the end of the first year. So there's nothing at time 0 that's a part of the annual series. So this is the form of annual series as it relates to present value. And here's the 10% factor table. But the weird one is related to the future value. And so this is the form of an annual series where, again, there's still nothing happening at time 0 because of the end of period assumption. For example, if we're going to be getting money, we assume that you get the money at the end of the first year. So this is a revenue. Maybe we're selling something. We're conducting business. We're getting our revenue from our clients at the end of the period. And what this problem would be asking us is, if you're receiving a series of payments over time, then what is the lump sum equivalent outflow in the same year as the last year of the annual series? And so future values occur in the last year of the annual series, rather than there being a year gap between them.
Is there a reason for that, or is it just because?
Honestly, I think it's because of the way that the formulas can be constructed, is that it's simpler if it is in the same year.
Okay.
Like if you look at the formula for F and A, let's go to this equation table. So this is the FA equation. It would be even more complicated an equation if there was that additional 1 year between them. So I think that's, as far as I can figure, that's why they're assuming that the future lump sum is in the same year as the annual series, is just so that the formula can be as simple as possible. Okay. Now, if you thought that was confusing, the fact that the future value is in the same year, gradients are even a little bit more strange. An arithmetic gradient is when the amount is changing by an increment that is constant over time. So for example, if you had to pay nothing next year, but then after 2 years you had to pay a certain amount, double that amount in year 3, triple that amount in year 4, so that gradual and steady increase over time, as long as the fixed increase quantity is the same, then that's a gradient. So an arithmetic gradient, it can either be an outflow or an inflow, but the form of it is that time 0 is the present, and 1 year from the present, or I guess I should say 1 period, because the periods don't have to be a year in duration. So 1 period from now, nothing happens, so that's 0g, but then you see the effect of the gradient starting in year 2. So we can have gradients where we're trying to find the present equivalent, or there can be gradients where you know the present equivalent and you're trying to find how much is it going to be increasing over time. So the key thing to remember is that the effect of the gradient is visible starting at the end of the second period.
So it takes it back 2 periods.
Yes, that's right.
You won't ever have one where the gradient starts in year 1?
No.
Okay.
And if you did, then what you'd do,
Just take it back a year at a time?
no, like let me show you a hypothetical where maybe you'd be tempted to think the gradient began in year 1. So let me draw a cash flow diagram here on the board. So we've got time, 1, 2, 3, 4, 5, 6, 7. Okay. Okay, so let's say it is so we have a gradient where at year 1, 2, 3, 4, 5. Okay. So if you were thinking if you were only thinking in terms of this as a gradient, then you'd say, well, I know that the gradient begins in year 2, so you'd maybe be thinking, do I need to go to -1? But actually, that's not what this is. What this is it's 2 things on top of each other simultaneously. This is an annual series and a gradient together. So what you should think of this is the annual series is $100 every year. And then the gradient, so, A is 100 and G is 100, but you see how here in year 2 is the first time that you see G. So here's G, here's 2G, here's 3G, 4G. So there's an annual series on top of a gradient. So it's actually following the form that we'd always expect, that you see the first influence of G in year 2. So here is 0G in year 1. So I think that's when you'd maybe see the effect of what appears to be the gradient in the first year, and the way to handle it is just treat it like an annual series with a gradient on top. Or, just because we're on the subject, looking to the future, what if it was 100, 200, 300, 400. Okay, so Ben, tell me what's your solution strategy here, where I say find P.
Take it to year 1 or take 1 to 0.
Pretty close. You take it to year 2, and then from 2 to 0. Because this is what we treat as our like quasi-present, year 2. Because, you know, this would be, there would be, once again, an annual series and a gradient.
Oh, so you couldn't do it because it's,
What's that?
well, it's like where it is an actual gradient, and then you have the 3-year gap, you couldn't take it back 2 years to year 0. 'cause
Oh,
it
okay.
takes you-
Yeah,
take it
okay. I
back
see your
to
point. No, no, no. You're absolutely right. Your first answer was correct. So you could just treat it like a gradient, so not an annual series and a gradient. You said initially take it to 1,
Yeah.
and then from 1 to 0.
Yeah.
You're right.
You
Yeah.
can do it the other way too, right?
Oh, you could, but your way's better.
Do more work.
Your way's better.
Okay.
All right.
And the A is gonna be 100 at 1 and 2. Like, how do we know?
What you would do is you would say find P given G, and so you'd find at year 1 what is the amount. So you'd say G is 100, N equals 1, 2, 3, 4, 5. N equals 5, and so we would go to the table and we'd find, let's say that this is 8% interest. I don't have, okay, here it is. Find P given G. So we would go to the PG, and we would want to know N equals 5. So it's 7.3724. So the ratio of P to G is 7.3724. Okay, so then P is our gradient quantity of $100 times 7.3724. Okay, so instead of 100 at year 3, 200 at year 4, 300 at year 5, and 400 at year 6, we're saying the economically equivalent of that is $737.24 at year 1, and then you take it from year 1 to year 0 using this one. Find P given F. And so then you'd further discount it by multiplying this 737 by 0.9259.
Does a gradient always have to start at year 0G? Like you have the 100, 200, 300. If you start at 300 and then just add 100, 400, 500, 600.
If it does that, then it's definitely an annual series underneath a gradient.
Okay, that was my question.
Yeah,
Okay.
yeah. So his question was, what I've been illustrating so far was that, it started at 0. But what if we had like 300, 400, 500, and then 600? Okay, in a case like that, then it's definitely this annual series of 300 each year, and then the gradient, so then 0G, 1G, 2G, and 3G. So year 2 would be our quasi-present, that we kind of take all of this to a lump sum at year 2, and then we can move it 2 more years back to time 0.
Okay. So
You
since,
take the gradient to year 1, right? And then the annual year 2.
No, the gradient would go to year 2, because this is 0G.
Oh, okay, yeah.
Yeah.
Oh, this is going to be convoluted.
No. You'll get the hang of it. I mean, this is like your first rep. It's not complicated. You'll get it.
so since there's no F given G or G given F, you have to translate it to a present value at like N equals 1, N equals 2, and then you do P to F to try to get it to a present value.
If we needed the future. So yeah, so like all I've been talking about so far is if we were finding the present equivalent of a gradient, but I don't think, if we look at the formula table, Okay, yeah, here is a formula for find f given g. So we could, if we wanted, find out a lump sum future. You don't have to take it to the present and then to the future. There is a formula that we could take it to the future directly if we wanted. So think about what kind of contract would actually involve a gradient, like in reality.
Like if the Fed's increasing interest rates by like 1% each year or 2% each year, that maybe that could go into play.
Yeah. So if you had a contract with someone and there was just an annual increase, like if you had laborers and you promised that you were going to give them a 5% raise each year, or like that their salary was going to go up by $1,000 every year, that could be an example of a gradient where there's a base starting today and then annual increases beyond that.
Student loan repayments.
Okay, that's another good one. Yeah. Okay, so we've looked at the form of annual series. We've looked at the form of gradients. I don't think I have any homework problems on this assignment that deal with gradients, but we will get to it in the third assignment. So,
I think number 9 is actually a gradient.
is it?
Yeah, it's.
I need to look at my assignments a little bit more carefully when I give them to you. Let's see.
I might be wrong, but I think it's increasing by 5%.
No. No, that's a find f given p.
Oh, okay,
Yeah.
my mistake.
That's right. Okay, so today's in-class exercise, let me give you this. We're going to get some practice today, and of course, it worked good last time where you're just kind of working on this together. If you feel like collaborating and if you feel more like you just want to chug through it on your own, that's okay too. Feel free to use the calculator on your phone, but not for exams. For the exams, you need to have just a standalone calculator that doesn't connect to the internet. Okay, so here's the question, the first one where I've done it according to the percentage way. On the whiteboard, I've also got the quantity way where you put the amounts. You'll get the same thing. I mean, there's no, as long as the weights of each category are somehow reflected, like the first category was, like this is loan, bank loan. So only 25% of your money is coming from the bank loan, whereas 45% of the money is from corporate bonds. And then the remainder, 30%, is from preferred stock. So the idea of a weighted average is that the bank loan shouldn't be counted as heavily as the corporate bonds because you're getting more of your money from corporate bonds, and so it's going to influence the interest rate. In our case, the corporate bonds have the lowest interest rate, and so it's going to bring the average down compared to if everything was weighted equally. So, we could have had 0.25, 0.45, and 0.3, and then divide by 1 instead of divide by 100. I mean, it's just, we want to make sure that we're somehow weighting the things. So there's the amount and the interest rate. All right. So that was the first question. The second one is just a cash flow diagram, just an illustration of how much your uncle can spend. So let me talk through this problem too and show you the illustration. So he's going to earn $247,000 each year for 5 years. And so there's an annual series, 1, 2, 3, 4, 5. So the annual series is $247,000. The overhaul at the end of the 3rd year, here is a future value, an outflow, because we're going to have to pay $55,000 for that. The fuel cost is $4,500 per year, so those are the small arrows that are pointing downward. And then there's this one lump sum inflow from selling the truck at the end of 5 years. So I kept it separate just so that we can see the influence of the different pieces together. So like this F is from selling the truck. Even though there was also some other money we got that year, that was the revenue for operating the truck. So I think this is a representation of the statement as a cash flow diagram.
Is it all right to put for the F the total?
The total 95,000 plus 247?
Mm-hmm.
Yeah, that's okay. I mean, for that matter, like if you were going to draw a net cash flow diagram, you could also subtract out the fuel costs, right?
Yeah.
If you wanted to.
Yeah.
But then if you also did that with this lump sum at year 3, then it would bring this annual series down and you would no longer have an unbroken annual series all the way through year 5. Because you've just got this one minor amount, the 55,000. So you'd have like an annual series in year 1 and 2, then a lower amount in year 3, and then so
Makes it harder. I got you.
yeah. But yeah, you could combine it together.
Okay.
Here's the answer to the 3rd one. If you've already solved that, it should be $3,512.95. I've got the solution to the 4th one up on the screen right now. So on part D and E, it's illustrating the difference in accuracy that you can have when you use the equation method versus if you're using a lookup factor. Because if you're using the formula and you have all of that precision in your calculator, then you know that the present value is $29,174.52. But if you are only using the 4-digit lookup factor, like P/F in the table is 0.5835. So if you multiply that number by 50,000, then you get 29,180. So that's a significant difference between the to the penny accurate number versus only here to the nearest $10.
But if I multiply that, I got 29,175.
That's what I got.
175, but you have to round it to the nearest $10 because
Oh.
there's 4 digits here. 1, 2,
okay.
3, 4. Yeah. So you do get 75, but rounding up because the dollar place is not significant. The tens is what is significant. Thank you for asking that, Victor. I'm glad you made that point because I should have shown that you get one number and then you round it
Yeah.
after making the decision.
That could be a point in the
Yeah.
game.
Yeah, that's right. But you won't make that mistake, right?
Not anymore.
Okay, good. Good. All right, it's 5:15. We're out of time, so when we pick up on Tuesday, we'll get to problems 5 and 6. I think probably you could solve them, but we'll still take a look at it on Tuesday of next week. So what you have in your laps right now is the next homework assignment. So you could make good progress on that over the weekend. I think you could solve maybe more than half of the problems on that assignment. So I'd encourage you to get an early start on homework number 2. And I will see you next week.
We're gonna be on that equation sheet for the exam,
Yeah, you will.
like that we did make our own.
Yeah.
Okay.